Hi again, this is still Steve Nuchtenburg and welcome to Weblecture 003. This is still part of the TU Delft course TI 1405, Computer Organization, or whatever name that and number that the course currently uses. And of course you can still access this through YouTube. So this is my last web lecture, at least for now, concerning binary numbers. But speaking of last lectures, you should really go and check out one by a guy named Randy Pausch. You can just YouTube it. I'll even put it in the description if you like. It's very inspirational and definitely worth watching. Anyway, today we're going to talk about some advanced binary arithmetic. Or alternatively, how adding a decimal point does not actually make anything more complex. But before we do that, let's take a quick look at what we've done during the last two lectures. So during the first one we discovered that there is actually other ways of counting, in addition to the decimal system that you're all familiar with, and we looked at how you can convert between those. Last time we discussed different notations for negative numbers. First of all, the sign and magnitude notation, which would have a sign bit and then followed by normal binary, if you will. Ones complement, which has a sign bit and then you flip all the bits if it's negative. So to give a quick example, sign and magnitude would have 0, 1, 0, 0 represent 4, 1, 1, 0, 0 minus 4, and ones complement would have 1, 0, 1, 1 represent minus 4. Two's complement takes the sign bit and then takes whatever is one's complement and it adds a 1 if it is negative. So, minus 4 in the two's complement would have the ones complement, which we just saw was 1, 0, 1, 1, and add 1, so you get 1, 1, 0, 0. Coincidentally, the same as the sign and magnitude. Please keep in mind, however, that 4 is the same in all three systems. In all three systems, it's simply 0, 1, 0, 0, because we only change things when the numbers become negative. Now, two's complement is the most popular and most useful, and we've also seen that Java also uses this. Now, today, unfortunately, we need to discuss one more notation, because of an organization called ITripleE. Even if you have not heard of this now, I can assure you, you will during the rest of your computer science careers. This last form of notation that we need to cover is the excess x notation. And, well, it's rather simple. We just have to subtract x from the normal binary to decimal conversion. So let's take a look here. Let's say we have excess 128 notation. Well, we take all zeros, which in a normal binary system would represent 0. However, in excess 28, we need to subtract 128. There is an excess of 128, meaning there is 128 too much in the number 0. So all zeros would represent minus 128. A 1 followed by only zeros is exactly 128 in binary. So, in the excess 128 notation, there is once again 128 too much, so we subtract it and we get 0. And then the largest possible number that we can create in these 8 bits is only ones. And there's no sign bit in excess 128 notation, so only ones would indicate 255 in a very simple binary to decimal conversion, and 255 minus 128 is 127. So the range that excess 128 covers is exactly the same as the range of two's complement, minus 128 to 127 for an 8-bit number. However, we can then also have, for instance, excess 5 notation. And excess 5 differs from 128 in only one very simple matter. Rather than subtracting 128, we need to subtract only 5, and then we will find a range of minus 5 to 250, something slightly different. And I hear you ask, why is this useful? Well, I was going to write down here, nobody knows, but, well, your book seems to disagree with that. Your book will tell you that it is because it allows for efficient comparison of relative size. And I guess there is some merit in this. You can easily see which number is the larger, but since there is no sign bit, so the first bit is already a very large indication, and as opposed to 2's complement, where you would really have to do the conversion. So yes, there are some benefits. So now that we know how XSX notation works, we can take a look at the IEEE floating point notation. And the IEEE floating point notation is basically a way to represent decimal numbers, like 1.5 or 2.33, in a binary form. IEEE defines a 32-bit floating point standard for this, with the first bit being a sign bit. Similar to how we've seen it before, 0 is positive, 1 is negative. Then we get an 8-bit for the exponent in XS127 notation. We'll take a look at what this means later. And then we have a 23-bit so-called mantissa. Now let's first take a look at how we would generally represent a float in binary. Let's say that we have the decimal 0.75. If we want to decode this into binary, well, let's first take a look at what the 7 and the 5 actually means. The 0, of course, is 10 to the power 0, the number of ones, in this case none. Then the 7 is the number of tenths, so the number of 10 to the minus ones, in this case 7 of them. And then the 5 is the number of 10 to the minus tenths, etc. So 0.75, well, let's convert that to binary, but now we only have 2 to the power 0, well, there's still none of those, there's no ones, and then the number of 2 to the power minus ones, the number of halves. Well, in 0.75 we can fit exactly 1 half, so we need to put a 1 over there. Then we have a quarter left, 0.25. Well, and lucky us, the next one is the number of 2 to the power minus 2's, which is quarters, and there was exactly 1 quarter left. So the binary equivalent of 0.75 is 0.11. Another example, 0.5 is just 0.1, 0.75 then is 0.11, and 0.1, well, you can try this one yourself. It's a bit more tricky because there is no simple binary notation for this. You will find that if you subtract the correct fractions of 2 from it every single time, you always have a little bit left, and so you get this recurring pattern of zeros and ones that seemingly has no end, similar to how a third in decimal has no end. It is 0.infinite threes. And so some simple fractions in decimal can be infinite and thus non-simple in binary. Well, now that we know this, let's take a look at 0.5 in IEEE notation. It's positive, so the sign bit is 0. This is the simplest part. Then 0.5, well, we've already seen that it's 0.1 followed by zeros. There is nothing else left. Now, how does it work in IEEE? What we need to do is we need to create a number where that spells out exactly 1 dot something. Nothing in front, so only zeros in front, and well, whatever we want behind that. So in order to accomplish that for our number, all we have to do is shift the 1 one place to the left. There is then only zeros in front, and whatever we want, in this case again only zeros, behind. One shift to the left means that if we want to reverse that, we need to have an exponent of exactly minus 1. We need to go back exactly 1 step. So what do we get? Well, we have the sign bit 0, and we have a mantissa of only zeros, because the mantissa is whatever remains after the 1 dot, so in this case all zeros. And we need to put the minus 1, our exponent, in XS127 notation, which means encoding 126, which is 0, 1, 1, 1, 1, 1, 0, 1. And there we have it, a 0 for the sign bit, an exponent, and a mantissa of only zeros. Now I can imagine that this example was a bit tricky already, so we're going to do one more, and it's going to be slightly bigger. It's going to be 128.125. Again, it's positive, so the sign bit is simply a 0. And now what we need to do is we need to see what would 128.115 be if we were to use the simple binary conversion. Well, 128 is a 1 followed by 7 zeros. Alright, so we write that down, then a dot, and then we need to decode dot 125 Well, fortunately this example is again rather simple. It's exactly 1/8, so 2 to the minus 3. So it's the third place after the decimal that we write down another 1. Now what we need to do is we again need to shift this to get 1 dot whatever we want. So in this case we need to shift it 7 places to the right. So we have an exponent of 7. It is 2 to the 7th, that is currently the first number. So if we shift that to the right to make it 2 to the 0th, our first number, our first 1. Then to get back, we need to multiply by 2 to the 7th. So the exponent is 7. The mantissa is then whatever comes after the dot. Well, it's 7 zeros, and then another 2 zeros, and then the 1 that represented our dot 125. So what do we need to do? Well, we can write down the sign bit, which is 0. We can calculate, quite simply, the exponent in excess 127 notation. So we need to decode the exponent, 7, in excess 127 notation, which means we have to decode 134 in normal binary, if you will, to get 1, 4 zeros, 1, 1, 0, and then we write down the mantissa. Well, it has to be made 23 bits, but we're only using 10, so we write down the 7 zeros, 2 more zeros, a 1, followed by a number of zeros. And there you have it, a conversion of 128.125 to the IEEE floating point notation. I really encourage you to try this with some other numbers. There's plenty of tools online that you can use to verify your answer. And also go the other way around. So you have a floating point number and you're going to go to the decimal notation. In this lecture, however, I'm going to move on to the last two topics of today. The first one is multiplication. And don't worry, we're not going to use the floating points in multiplication right now. We're just going to use nice round numbers. And it's rather simple, really. Let's take a quick look at how you would do this in decimal. Well, my grandpa actually taught me this, and he taught me that 25 multiplied by 25 can be easily calculated as follows. You first take the last number of the bottom one, in this case a 5, and you multiply that with the 25 above, which is 125. Then we continue. The 20 times 75 is 500. You add them together and you get 625. Well, binary has only ones and zeros, so it's even easier. Let's say you have 0, 1, 1, 0, and we're going to multiply that by 0, 0, 1, 1. Well, what you do is you multiply the 1 times 0, 1, 1. Oh, you write it down. Again, only now there should be an extra 0 at the end because we've shifted one place to the left. Add them together and we have our answer. Keep in mind, however, that unlike addition, in binary it's very, very common for the answer not to fit in the same number of bits. In this case, we multiplied two 4-bit numbers and already the outcome was a 5-bit number. So this works fine, but it gets a little more complicated when we throw negative numbers into the mix, because we need to use sign extensions. 2's complement says that 0, 1, well, is the same as an infinite number of zeros followed by 1, and it's plus 1. It also says, however, that 1, 1 is the same as any number of 1's, and it's equal to minus 1. And this is crucial. So what we can do for any positive number, we can add however many zeros we want in front, and for any negative number, we can add however many we want ones in front. This is what we call sign extension. So let's take a look at an example. So we have two binary numbers here, and we're going to multiply these together. First, we start with a 1 all the way at the right, so we can simply copy the operand. Then we have two zeros, so we can write down absolutely nothing. And then for the next one that we find in the bottom operand, we need to copy the top operand again, only shifted 3 places to the left. Now we want to add these together, and you'll find that the top one has less digits than the bottom one. So we're going to use sign extension to make sure they have the same amount of digits, and we're going to add them together then. And the answer then will also be sign extended, but we can just leave out the extra ones. Now let's convert both the operands and the answer to see whether the math we did is correct. I made a small mistake while doing this, so it should not read minus 112 but minus 102. And then there is the 9 So minus 102 times 9 is indeed minus 918. Now this is rather simple because there was only 2 1s in the bottom operand, so that we only had to do one addition. But imagine multiplying by 0, 1, 1, 1, and you would suddenly have to do a whole lot more work, because there are multiple additions to do. Fortunately though, we're not the first to encounter this problem, and we're not the first to be lazy. So let's have a guy called Boov save our day. This method, well, it makes this stuff rather easy. We simply use some simple math to reduce our simple math. Let's say that we have 0, 1, 0, 1, 1, 0, and we want to multiply that by 0, 0, 1, 1, 1, 1, 0. It's 4 multiplications. But these 4 multiplications we then need to add together in 3 additions. What we also could do, however, is we could write it down as follows. We could say, well, we leave the top part the same, but the second number, we're going to replace it with 0, 1, 0, 0, 0, minus 1. Now, of course, minus 1 doesn't really exist in the binary system, at least not with the minus sign, but by allowing it in our multiplication here, all we have to do is 2 non-zero multiplications and only 1 addition. So what we in general do is we replace a sequence of x 1s with a 1, then x minus 1 zeros, followed by a minus 1. And let's take a look at how that works. So let's take our example we had just now, and let's do that little trick where we change a sequence of 4 1s to a sequence of 1 followed by 3 zeros followed by a minus 1. The first multiplication we encounter is minus 1 times the top part, the top number. Well, minus 1 times a number is basically just making it negative. So all we need to do is find the 2's complement of the number at the top and write it down using a sign extension if necessary. Then we need to shift a couple of places to the left and we find a 1. Well, this is simple, we just copy the number that was already there. We add them together and we're done. This is it. This is the answer. And well, without really trying to figure out whether our math was right, we can already see that we multiplied 2 positive numbers and the result is again positive. Feel free to check my math here, I might have made a little mistake, I don't know, but this is the way to do it. And you can see that this saves us quite a few additions. Rather than doing the 3 additions that were necessary at first, we can do it now with only a single addition. And especially in 32-bit numbers, I mean this is only 7 bits and already there were 4 multiplications, thus 3 additions. But in 32 bits there can even be 31 multiplications and thus 30 additions, for instance. And if we can reduce that to 1 addition, that really saves us or a computer a lot of time. So the final topic, we're finally there, is division. And it's something that, well, a lot of people are having trouble with, but it's basically because they're not able to do a normal division in decimal either. And we're going to use what in English we call a long division method, or in Dutch we call a staartdeling. Let's say we have our example overview. We have 625 and we want to divide that by 25. Here's how long division works. We take a look at whether the 25 would fit in the very first number, a 6. Well, obviously it doesn't. So what do? We get the extra number involved. So now we have 62. Does 25 fit in there? Yes, it does. And it fits in there exactly twice, for 50. So 2 will be the first number of our answer, and we subtract 50 from 62. We then have 12 left, and in 12, well, it doesn't fit anymore. So what do? We drop down the next digit, which was a 5. We have 125. Does 25 fit in there? Yes, exactly 5 times. And now we have 0 left. And then we have our answer. 625 over 25 is exactly 25. In binary, this works exactly the same. Let's say we have 11011000 and we want to divide that by 1100. We start with one digit, 1. Does it fit in there? No, it does not. Does it fit in 11? No, it does not. We drop down another digit, 110. Still doesn't fit. 1101. Ah, now it fits. So we subtract 1100 from this, 1 for our answer, and then we drop down the next digit, 1 1. Does it now fit? It does not, so we write down a 0. We drop down another digit, 1 1 0. Does it now fit? It does not, so we write down a second 0 for our answer. We drop down another digit, now we have 1 1 0 0. Does it fit? Yes, exactly once, so we have 1 0 0 1. And there's our answer then. 1 1 0 1 1 0 0 divided by 1 1 0 0 is 1 0 0 1. Let's have one more example to finish this with. 1 0 1 0 1 0 1, and we divide that by 1 1 1. Well, it doesn't fit in the first one, it doesn't fit in 1 0, it doesn't even fit in 1 0 1, but it does fit in 1 0 1 0. So we subtract from that 1 1 1, write down 1 for our answer. What do we get? Well, we get 1 1. We drop down the next digit, which is a 1. It fits exactly. So we write down a 1. We have 0. That won't fit. We drop down another 0. Still won't fit. We drop down the 1. And unfortunately, it still won't fit. So what do we do now? We have 1 left, and there's no more digits to drop down. Well, we can do either one of two things. We can say, well, actually, there are many digits left. There is a decimal point here, and there are an infinite number of zeros behind. We can use as many of those as we need until we get a right answer. Yeah, we could do that, but, well, we could also say that this division simply has 1 left. There is a remainder of 1. So there is a remainder of 1 over 1 1 1. And, well, with division also covered, this mini-series for the TI 1405 course is now over, and I hope you've learned something about doing addition in binary, octal, and the hexadecimal system, how to convert between decimal and binary, and also between binary and octal and hexadecimal. And keep in mind that if we want to go from decimal to, for instance, octal, I always find it easiest to go through the binary system. We've also seen how to do subtraction in binary and how to represent negative numbers in binary using the sign and magnitude, 1's complement, 2's complement, or even the XSX notation. Then we've taken a look at the floating point notation, more specifically the IEEE one. And we've taken a look at multiplication in binary, and we used Booth's algorithm there. We've taken a look at division in binary system using the long division method. And perhaps you've also seen that some things, no matter how complicated they may seem at first, are really rather simple if you can just relate them to something you've done before, whether it is the way of counting, whether it is long division. Anything can become a trivial task, a simple task, as long as you can relate it to something that you already know how to do. If you have any questions regarding anything I said in these 3 lectures, feel free to contact me, either through YouTube or find my TU email address if you study there. My name is Stefan Huchtenburg. I've spelled it out 3 times. You should be able to find my email address with any questions you might have. For now though, I wish you goodbye, farewell, and good luck with the TI 1405 course or any other course you might be doing for your studies. Goodbye.